Have you ever looked at a complex logical statement and just thought, there has to be a simpler way? Well, there is. Today, we're going to unpack a really elegant and powerful tool for doing just that. It's called De Morgan's laws. But let's start with a little thought experiment. Imagine you wanted to find the exact opposite of a group of things. Say you're looking for everything that is not a cat or a dog. How would you even describe that? It's not as straightforward as it seems. And that's exactly the kind of puzzle De Morgan's laws are built to solve. So here's our game plan. We'll start with some basic tools from set theory, then we'll unveil the laws themselves, and after that, we'll put them to work simplifying expressions and even solving a problem with a Venn diagram. Okay, let's dive right in. Before we can really wield De Morgan's laws, we need to make sure we're solid on three fundamental ideas in set theory. Think of these as the essential tools in our toolkit. First up, we have the union. You'll see it with this U symbol. This is basically the OR of set theory. The union of A and B is everything in A, everything in B, and anything they share. It's like you're throwing them all into one big pile. Next is the intersection, which looks like an upside-down U. This is our AND operator. The intersection of A and B is only the stuff they have in common, the elements that are in both sets at the same time. It's just that specific overlap. And finally, the complement. You'll usually see it with a little dash or a prime symbol. This one's easy. It just means not. So the complement of A is everything else in the universe that is not in set A. Simple as that. Now, complements have some really useful properties. For example, if you combine a set with its complement, you get the entire universe. If you look for the overlap between a set and its complement, you get, well, nothing. But I want you to pay close attention to this third one, the double complement. If you take the complement of a complement, you just end up right back where you started, with the original set A. Trust me, this little trick is going to be our best friend in a few minutes. All right, now that we have our toolkit, it's time to reveal the main event. These are the two powerful laws that give us a blueprint for simplifying those tricky not everything statements. And here they are. So what's the big pattern here? Notice what happens when you take the complement, that little prime symbol, of an entire group. It's like you're distributing it to each set on the inside. But here's the crucial part. The operator in the middle flips. A union becomes an intersection, and an intersection becomes a union. A really easy way to remember this is break the line, change the sign. Theory is one thing, but seeing these laws actually work is where it gets fun. Let's start with a pretty straightforward example just to see how it operates. Okay, so our task is to simplify this expression, the complement of the group X complement union Y. So let's break it down. First, we apply De Morgan's law. We push that outer complement inside to both the X prime and the Y. And what's the rule? The union in the middle has to flip to an intersection. That gives us X double prime intersected with Y prime. And right away, you should spot that double complement on the X. We know two knots cancel each other out, so that just becomes a plain old X. And there we have it, our much cleaner final answer, X intersect Y prime. Awesome. Let's level up just a little bit. What happens if we have three sets inside? Don't worry, the principle is exactly the same. We do the exact same thing. The outer complement gets distributed to A, B prime, and C prime. And you guessed it, both of those union symbols flip to intersections. That leaves us with A prime intersected with B double prime, intersected with C double prime. And look at that. We get to use our double complement rule not once, but twice. Both B and C simplify back to their original forms, leaving us with a final answer, A prime intersect B intersect C. Okay, you've definitely got the basics down. So now it's time to tackle something a bit more complex, where De Morgan's law is just the first step of the puzzle. Take a look at this one. We've got operations inside of operations, all sitting under one big complement. The key here is to stay calm and work from the outside in. We'll start by breaking that big outer bracket. Okay, let's be methodical. Step 1, apply De Morgan's law to that main intersection in the middle. This breaks the expression into two parts and flips the sign, so we get the complement of the first group union the complement of the second group, which is P prime. Now, look at that first part. We have another chance to use De Morgan's law. So let's apply it again. We push that complement inside, giving us P prime intersect Q double prime. Now we can simplify that double complement, which just turns back into Q. So we're left with P prime intersect Q union P prime. Now,
Pause for a second and really think about what this says. The first part is the piece of Q that is also not in P. Well, by definition, that little slice of Q is already entirely contained within the bigger set of P prime. So when you unite that small piece with the entirety of P prime, you just get P prime. It's like pouring a cup of water into a lake. You still just have a lake. The whole thing collapses down to just P prime. Look how that complicated expression just melted away. So far, we've been all about the symbols and the algebra. But sometimes the best way to really get a feel for set theory is to just see it. Let's switch gears and use a Venn diagram to solve a problem. The absolute key to not getting tangled up in a three-circle Venn diagram is to have a strategy. And the best one is simple. Always work from the inside out. Start at the dead center where all three circles overlap, and then build your way outwards. So let's apply this. Imagine a survey of 70 investors. We know how many invested in bonds, shares, and assets. We're also given info about the overlaps. The most important piece of data to start with is this. 7 investors held all three. So let's put that number 7 right in the bullseye of our diagram. Okay, now we build outwards. We're told that 10 people in total invested in both bonds and assets. That's that entire lens-shaped area where the two circles overlap. We already know 7 of those 10 are in the very center. So the remaining part of that overlap, the part for people who are only in bonds and assets, has to be 10 minus 7, which is 3. Let's keep going with the bond circle. The survey said the total number of bond investors is 30. We want to find the number who are only in bonds. To do that, we take the total of 30 and just subtract all the little pieces inside that circle that we've already figured out. So we subtract the 3, the 7, and the 8 who overlap with other sets. That's 30 minus 18, which leaves us with 12. These are the investors who are exclusively in bonds. Okay, so once we repeat that process for every single region, we can add up all the numbers inside the circles. And if you do that, you get a total of 61 investors. But wait, the survey was of 70 people. So where are the rest of them? They're outside the circles. We just subtract. 70 minus 61 gives us 9. And that number, 9, is a perfect visual of the complement of the union of all three sets. So there you have it. We've seen how to break down these complex not statements using algebra and how to actually visualize them with diagrams. De Morgan's laws give us a clear, logical way to turn confusing negations into much simpler, more manageable pieces. The only question left is, what complex statement will you simplify first? Hey everyone, and welcome. Today, we're going to crack open one of algebra's coolest shortcuts, the binomial theorem. It's this amazing tool that takes something that looks like a total headache and turns it into a really simple, clean pattern. So take a look at this thing right here. 3 plus 9x to the power of 5. Can you imagine trying to multiply that out by hand? It'd be a complete mess of terms. It'd probably take up pages and pages of paper. And that is the exact nightmare the binomial theorem was born to fix. By the time we're done here, you'll see exactly how to tackle this, no problem. Okay, so here's the game plan. We'll kick things off with why we even need this theorem. Then we'll figure out how to find the most important numbers, called the coefficients. After that, we'll build the theorem for whole numbers, stretch it to cover fractions, and finally see how it lets us do some seriously cool approximations. All right, so first up, let's really dig into what this problem is all about. We all probably remember from school that a plus x squared is a squared plus 2ax plus x squared. Simple enough. But what about to the power of 3? Or 7? Or, I don't know, 10? Yeah, that's when things get ugly fast. I mean, if you actually try to multiply out a plus x 7 times by hand, you'd be there all day. And it is so easy to make one tiny little mistake that just blows up the whole thing. So what we really need is a system, right? A reliable pattern we can trust every single time. And that's exactly what this theorem gives us. So the secret to this whole pattern, it's all about the coefficients. You know, in a squared plus 2ax plus x squared, the coefficients are 1, 2, and 1. They're just the numbers out in front. The million-dollar question is, how do we figure out those numbers for any power without doing all that crazy multiplication? Turns out there's a formula for that. Well, it's called the binomial coefficient, and you'll see it written as NCR. In math, it's all about counting the number of ways you can combine stuff. In our formula, n is just the power we're expanding to, and r is the term we're on, starting from 0.
And that little exclamation point, you've probably seen it before, that just means factorial. All it means is you multiply that number by every whole number all the way down to 1. So, 3 factorial is just 3 times 2 times 1. Easy. Okay, let's actually do one. Let's calculate 5c2. So n is 5, r is 2. We plug them into the formula. That gives us 5 factorial over 3 factorial times 2 factorial. Now, when you write out all the numbers, you'll spot this really neat shortcut. See how the 3 times 2 times 1 on the bottom is also on the top? We can just cancel them out. That leaves us with a much friendlier calculation. 5 times 4 on top, divided by 2 on the bottom. And that gets us to 10.
Okay, awesome. So now we know how to get the magic numbers, the coefficients. Let's put it all together and build the full theorem, at least for positive whole numbers. And here it is, the master recipe. For any positive whole number n, this is the pattern. Now, look closely at the pattern here. It's actually pretty cool. The power of a starts high at n, and then steps down by 1 each time. Meanwhile, the power of x does the opposite. It starts at 0 and climbs up by 1. And the number in front of every single term, that's just the binomial coefficient we just learned how to find.
Okay, now here's a pro tip. Things get way simpler when that first term a is just the number 1. I mean, think about it. 1 to the power of anything is always just 1, so a bunch of stuff in the formula just kind of disappears. This gives us a much cleaner version of the formula that is super useful, and it's the one we're going to use for most of what comes next. All right, let's put this to the test. We're going to expand 1 plus 2x 4. This table really breaks it all down for us. Let's just zoom in on term 3 for a second. The coefficient is 4c2, which we calculate and find out is 6. Our first part, 1, is squared, but that's just 1. Our second part, the 2x, gets squared, which gives us 4x squared. So you just multiply those 3 pieces together, the 6, the 1, and the 4x squared, and boom, you get your term, 24x squared. You just follow that same process for every single term. Okay, so far, everything's been pretty straightforward, right? Our power n has been a nice friendly whole number. But what happens when we throw a curveball in there? What if the power is a fraction, like 1/2, or even a negative number? Well, the theorem still works, but it comes with a couple of really interesting new rules. So the formula looks almost exactly the same, but you gotta notice those 3 little dots at the end. That's a huge deal, because when n isn't a positive whole number, this thing doesn't stop. It becomes an infinite series. It just keeps going and going and going. And that leads us to a really, really important new condition. And this is probably the most important new rule to remember. This slide breaks it down perfectly. When n is a whole number, you get an exact answer with a set number of terms. But for fractions or negatives, it's an infinite series, which means it's an approximation. And for this to even work, for this sum to actually settle on a real number, there's a critical catch. It's only valid if the absolute value of x is less than 1. If it were bigger, every term would get larger and the whole thing would just shoot off to infinity. So that rule is absolutely key. Okay, let's try 1. We're going to find the first 3 terms for the square root of 1 plus 2x, which is just 1 plus 2x to the power of 1/2. The first term is always 1. For the second term, it's n times x. In our case, that's 1/2 times 2x, which just gives us x. Then for term 3, we plug into that next piece of the formula. The coefficient part gets a little messy, but it simplifies down to negative 1/8. We multiply that by our 2x term squared, which is 4x squared. So negative 1/8 times 4x squared gives us negative 1/2 x squared. Put it all together, and our approximation begins 1 plus x minus 1/2 x squared, and so on. Okay, so you might be thinking, this is cool math, but what's the point? Well, now we get to the really powerful part. This whole infinite series thing isn't just a party trick for mathematicians. It's a real tool for making calculations that would feel pretty much impossible otherwise. I mean, let me ask you this. Could you figure out the square root of 101 in your head without a calculator? It sounds impossible, right? But with the binomial theorem, we can get amazingly close. Okay, check out this clever trick. The first thing we do is rewrite 101 as 100 plus 1. Why? Because 100 is a perfect square. We can pull that 100 out of the square root, and it becomes a 10 on the outside. And this leaves us with 10 times the square root of 1 plus 0.01. And would you look at that, the thing in the parenthesis is in that perfect 1 plus x to the n form we need, where x is 0.01 and n is 1/2. So we just apply our series formula to that part and then multiply the whole thing by 10 at the end.
And there you have it. Just using the first 3 terms of our series, we get about 10.0499. The actual value is about 10.04987. I mean, come on, that is ridiculously close. We just did that with a few steps of basic arithmetic. That, right there, is the power of this theorem. So think about what we just did. We went from just expanding some simple brackets all the way to calculating the square root of a weird number with incredible accuracy. The binomial theorem proves that there are these beautiful, deep patterns hiding right under the surface of the algebra we all learn. It really makes you wonder, doesn't it? What other amazing shortcuts and patterns are just waiting to be discovered in the math we use every day?